All right, let me start with questions. Does anybody have a question? All right. I postponed the homework because I was slow putting it on the web page. So the homework that was due Thursday is now due next Tuesday, a week from today. I've also extended the notes, and in particular I figured out last night how to do Feynman diagrams in LaTeX. It turns out that a graduate student by the name of Joshua Ellis wrote a rather nice package called TIC-ZK. I forget what, let me see, what's the name of it exactly? It's TIC-Z-Feynman. And in order to run it, though, you have to run it with not LaTeX, but Lua LaTeX or Lua Tech, either one. And it makes very nice looking Feynman diagrams. So that's what I recommend. There's a conflict, however, between Lua LaTeX and color, and so you have to somehow cope with that. I just deleted all references to color. All right, so the topic for today is Feynman's rules, and Weinberg basically states them, and I think I'll sort of state them again in slightly different terms. So the first thing you do is you draw the diagrams. And you label the internal lines with the full momentum that flows through them. And so label lines. The second thing is that each vertex, and so far we've had diagrams with one or two vertices. With each vertex you get a factor, a minus I, a 2 pi to the fourth, a coupling constant associated with the vertex, and a delta fourth, which is a sum of all incoming minus outgoing momenta. So 4 momentums conserved at every vertex, because a vertex in the space-time sense is just an x or y or z, one of the, or an xi, and you integrate over all of xi for space, and so that produces a delta function. And the xi only occurs in the exponential. It doesn't occur anywhere else. Consequently, you always get a delta function that conserves full momentum. For each outgoing line, so each outgoing line gives you a factor U star L, P, S, and if I follow his notation religiously, N is a particle type index. So this might be electron or up quark, red up quark, or something like that. And for each outgoing, so for outgoing fermion or particle, you get a star. For outgoing antiparticle, no star, and you get V rather than U. And so this is P, S, N. And because they're outgoing, they typically have primes on them. And again, 2 pi to the 3/2.
What do you mean going from the top? What do you mean going from the top?
Well, Weinberg likes to draw diagrams like this. In fact, I'm going to draw a diagram that this is a diagram that we'll analyze later. I could not get Tick Z, Feynman, to draw it that way. But Weinberg has time going this way, and so you've got your, so these are the outgoing particles are going out the top, and the incoming particles are coming in from below. On the other hand, most people draw this diagram this way. With incoming particles here on the left, outgoing particles on the right. And what this is an incoming fermion, an incoming antifermion. And so in Weinberg's way, it's like this. Most people draw it this way, and in fact, the software that I use to draw the diagram in the class notes, I could not get it to draw this. It does not like, it likes to make vertices with 3 angles separated by 120 degrees. Each angle is 120 degrees, and I don't know how to get it to do that. If you find out how to do it, I may, send me an email or something. So the conventional way is incoming, outgoing, and here, out is at the top, incoming is on the bottom. So these are outgoing lines, incoming lines. It's either UL or PS and N, 2 pi to the 3/2, or VL star of PS and N over 2 pi to the 3/2. So those are the external lines, and once again, there's the software Tick Z-Feynman, which allows you to draw rather nice Feynman diagrams in LaTeX, but you have to use Lua LaTeX. What Lua means, I don't know. Each internal line so for each internal line, line for a scalar boson, what you do is you have minus I over 2 pi to the 4th, 1 over whatever the momentum is, q squared plus the square of the mass of the internal particle, of the particle going across the internal line. So for example, here, this would be momentum q, and whatever that momentum is, it goes there. Whatever the mass of that particle is, it goes here. So that's an internal line. If, on the other hand, the internal line is a fermion line. So for example, this Feynman diagram where P plus K goes to K prime plus P prime. Here the internal line is a spin 1/2 particle, and there you put in minus I over 2 pi to the 4th. It would still be Q squared plus ML squared minus I epsilon. But in the numerator, we've got the more complicated factor, minus I Q slash plus M beta. And then, in fact, since that's a matrix, it's the LM matrix element. And if it's a spin 1 particle, on the other hand, so for example, if we have a particle, fermion-antiparticle, fermion-antifermion goes into photon, goes into fermion-antifermion, you draw a wavy line and you write, and it contributes a factor I over 2 pi to the 4th, eta Lm plus PL PM over M squared. Well, actually it's Q, that's a typo. Over again, Q squared plus ML squared minus I epsilon. And okay, so, and in the case of, you might worry, what about the photon? You take M going to 0, this is a pretty singular limit here, and that's absolutely true. What happens in the case of the photons is this term doesn't appear. We'll see that later. So step 2 is a very, very big step. Step 1 is just a couple of sentences. Step 2 is fairly big to describe at least. 3 is integrate over everything. Over all momenta. And of course sum over L, M, and so forth. And then 4 is add all Feynman diagrams. Okay, so that's Weinberg's statement of the Feynman rules. I've never particularly liked the idea of following the Feynman rules directly. It seems to me that if you just do Dyson's expansion based on first principles, the Feynman rules occur just naturally, and in any case there are going to be combinatoric factors, getting the indices right and so forth. I don't know if there are such obvious rules for that. What happens though is that if you are working on a particular physical process, you'll be writing down the Feynman diagram, and you do the Dyson expansion 2 or 3 times. Well, you then develop an instinct for just writing down the diagrams, and you can write down the you can go to step 3 almost immediately with a little experience, and what you're doing is you're essentially following these Feynman diagrams and inputting your experience. So let's see how this happens for a Hamiltonian density of interaction. So let me just write it like that. And I'm calling it GLM psi L dagger of x psi m of x phi of x. So this is a scalar field, a neutral scalar field interacting with a fermion, which I'll nominally say is different from its antiparticle. So particle fermion-antifermion there. And I want to do the case that's really that became of enormous importance, I don't know, 40 years ago, when colliding beam accelerators were first developed. I suppose the first one was at SLAC, and one of the amazing things is the amount of physics that people at Stanford managed to get from their they started out with an electron accelerator and then realized that they could create and accelerate positrons very easily. So then they had an E plus E minus collider, and they discovered more physics than virtually any other. I mean, the amount of physics for the amount of dollars that were put in was a higher yield rate than anywhere else. And then, in fact, the lowest yield rate is the LHC, because you've got an enormous amount of investment, and the only particle discovered so far is the Higgs. On the other hand, the exploration of a whole range of energy without anything showing up, that is a result. It tells you there are no particles in a whole range, and it also tells us that if nature cares about supersymmetry, it hides it until very high energies. What that means, I don't know. All right, so the initial state then is going to be a fermion of momentum P and spin S, or Z component of spin S, and an antifermion of momentum Q and spin T. So this is A dagger of P and S, B dagger of Q and T on the vacuum. By the way, in the notes of on Weinberg's chapter 6 class notes, I sometimes use B for boson, even though I was also not in the same problem, but we're often using B for the antiparticle creation and annihilation operators. Okay, so that's the initial state. The final state is P prime, S prime, Q prime, T prime, and this is vacuum B of Q prime, T prime, A of P prime, S prime. And the lowest order amplitude then is A is equal to minus 1 over 2 factorial integral d4th x, d4th y, vacuum B of, all right, there's a typo. B of Q prime and T prime, A of P prime, S prime, time-ordered product of the two Hamiltonian interaction Hamiltonian densities. And then here, let me put it this way. A dagger, P and S, B dagger, Q prime, no, P prime. P prime, S prime on vacuum. Wait a second, I've got to get this notation a little bit more standard. P and S, Q and T. Right, okay. All right, well, the amplitude then is the same thing when we put in what these Hamiltonian densities are. We have, let us say, GLM, GL prime, M prime, and then we have psi dagger L of X, psi M of X, phi of X times psi dagger L prime of Y, psi M prime of Y, phi of Y, and then a dagger of P and S, B dagger of Q and T vacuum. So that's what we've got. And then, as usual, we cancel the 2 factorial by choosing to have the incoming particles, in this case, annihilated at the vertex Y instead of at the vertex X. So in other words, I'm going to say that this is, well, the diagram actually looks like this. A dotted line is what people normally use for scalar particles, and this will be carrying momentum P plus Q. So this could have been vertex, space vertex X, and this Y. I'm choosing this to be Y and that X, so 2 is canceled. And what we get then is that A is equal to minus GLM, GL prime, M prime, over, and now it's 2 pi to the 6. That comes, if we use these Feynman rules, you see you've got 4 external lines. So you've got 4 factors of 2 pi to the 3 halves. That's 2 pi to the 6. And then you've got this integral d fourth x, d fourth y, vacuum u star L of p prime s prime, v star m, q prime t prime. No, there's a mistake there. In fact, the Feynman rules are very useful, actually, even though I was disparaging them earlier. The Feynman rules are very useful because they help us keep track whether we put a star on the U or on the V. If it's an outgoing antiparticle, no star on the V. Incoming antiparticle, star on the V. So this is...
By incoming, you mean like coming into the vertex?
Yes, coming into the vertex, but coming into the process. In other words, there's an initial state and a final state.
So
The initial state is consists of the incoming particles. The final state consists of the outgoing particles. This is a scattering experiment.
Yeah.
Incoming, outgoing.
So would you call Q prime an outgoing antiparticle or incoming antiparticle?
P prime is an outgoing particle.
What about Q prime?
Q prime is an outgoing antiparticle.
Okay, so it's still
Antiparticles have everything backwards, and Feynman used to startle people by saying that we can think of them as going backwards in time. Now, I will not elaborate on that. There may be more there than we think, but that'd be the subject of another study. Okay, so I've got a couple of typos here. So the outgoing should be a V here. So this is not V star, but this is V. And these were both added in at X. And so we get the factor e to the minus Ix p prime plus q prime. We're then left with the time ordered product of phi of x, phi of y, the scale of particles. And then we have the O. Okay, UM prime of P and S, the incoming fermion and the incoming antifermion. Why did I write things backwards? All right, let me get straight these indices. I may have screwed up the indices. We have LM, L prime, M prime. So the indices are L prime and M prime, but it's psi M prime, and psi, of course, will be e to the I py a u m prime plus e to the minus I py b v m prime. That's the field, and then the adjoint field, which was psi dagger L prime, right, at y, would be e to the minus I py a dagger u star m prime plus e to the I py. All right, I may have screwed up here. No, this is b dagger, and that's v. So this is v star L prime, and this is an L. This is wrong, tell me. Check it on your own and tell me if it's wrong. Okay, so the field psi m prime is the one that annihilates this incoming spinner, and then this one is v star. The psi dagger is going to annihilate the incoming antifermion, so it is V star L prime. And let's just check this one. Here we have psi dagger L, and that creates the outgoing fermion, and so that's this term, and then the field that it's then, this is a U star, and okay, now I don't remember what the rule is. I think, all right, remind me, is this V or V star? Okay, it's U and V in the field, and where the hell are my notes? Up here. So, this was right. A, B dagger, U, V. So it's A dagger, B, U star, V star. And so in particular, the psi L is creating the psi dagger L is creating the outgoing particle, so it's UL star, and that's an L, and then the psi M is creating the outgoing one, and so that's VM. Okay, so this all seems to be right. So this is Q and T, and then this is e to the I P plus Q dot Y, and then there's a vacuum state at some point. Okay, so that's the amplitude. And now the scale of propagator means that we put in an integral over K, and so what we have is minus GLM, GL prime, M prime, and 2 pi to the 6th, integral d fourth x, d fourth y, and we have a d fourth k for this propagator. We have U star L of P prime, S prime, B star M. So this should be B star M. Okay, now let's get this straight. Which is it? Is it B star? Ah, it is VM. Okay, so there was a typo here in my notes. So we decided carefully that it was VM, and that fixes something that bothered me later on. Okay, so this is VM of Q prime and T prime, e to the minus IX, P prime plus Q prime. And then this time-ordered product here brings in a minus I over 2 pi to the 4th, and a 1 over k squared plus m squared minus I epsilon over the I epsilon, it doesn't matter. And this is e to the ik x minus y. And again, whether it's x minus y or y minus x doesn't matter in the case of scalar and vector bosons. It only matters for the fermions. That's why fermion lines have an arrow, and well, charged boson lines sometimes have an arrow for the charge. Anyway, what's left then here is UM prime of P and S, B star L prime of Q and T, and e to the I y P plus Q. All right, so if we put all this together, what we get is that, notice that x and y occur only in the exponents, and they occur in, there are 3 exponents altogether, and one exponent just has x, one exponent just has y, and then the propagator exponent has x and y. And those then give us the integral over of this Fourier factor over all of space-time gives us 2 pi to the 4th times the delta function, and so 2 pi to the 10th, when it gets knocked down, producing 2 delta functions, brings us down to 2 pi squared, The i's give us I here, GLM, GL prime, M prime, and now it's just 2 pi squared. And we have integral d fourth k, and we have UL star of P prime, S prime, VM of Q prime, T prime, delta fourth of K minus P prime minus Q prime, delta fourth of P plus Q minus K, times use of M prime of P and S, V star L prime of Q and T. And then the propagator factor 1 over K squared plus M squared minus I epsilon. And this M is the M of the boson, not the mass of the fermion-antifermions. So when we do the integral over K, this delta function sets K equal to P plus Q, so this becomes P plus Q squared. And the other delta function, K is replaced by P plus Q, so this just conserves energy, energy and momentum for the whole process. And so altogether then, the amplitude is I delta fourth P plus K minus P prime, whoops, P plus Q minus P prime minus Q prime. And then it's, I'm going to write this way, U star L of P prime S prime, GLM, VM of P prime T prime, and then I'm going to write this again, I'm going to interchange the V's. V star L prime of Q and T, G L prime M prime U M prime of P and S, and then this is divided by P plus K, P plus Q squared plus M squared. And this is 1 over 2 pi squared. Notice that the indices work out in such a way that we can use matrix notation. And so what we have here is I delta fourth of P plus Q minus P prime minus Q prime, 2 pi squared, U dagger of P prime S prime G V of Q prime T prime, V dagger of QT U of P and S to G, sorry, that's the important thing, P plus Q squared plus M squared. And as I said, the I epsilon in tree diagrams is always ignorable. And in fact, it would have to be ignorable because the whole point of the I epsilon is to tell you how to use that rule for dealing with complex contour integration. The principal part rule, Cauchy's principal part. But if you don't have an integration, then you don't need an I epsilon rule. And so in tree diagrams, you're done with in tree diagrams, you're left with an I epsilon, no more integration, so you drop the I epsilon. So this shows you how the Feynman rules work, and I would say then that if you find yourself computing Feynman diagrams, if you do a few of them, you'll find the Feynman rules helpful to get complex conjugates and 2 pi's and so forth right. If you start though doing, after you've done many, many Feynman diagrams from scratch, you then find that you can just write down the diagram and write down the answer almost immediately. Now when I say write down the answer, that doesn't mean you're done. In this case, for example, you'd want to get to a cross-section. And so you have to go through the same thing that you have in quantum mechanics that takes you from an actual amplitude to a cross-section. So here there's only one diagram. If you have fermion-antifermion goes to fermion-antifermion, for this type of interaction there's only one diagram. But in general there are 2 or 3 diagrams. You have to add the amplitudes together. That's the way quantum mechanics is, of course. And the reason is that you have initial state, final state, e to the minus I ht, and you're expanding this. This gives you a bunch of Feynman diagrams. This is the amplitude. There's a sum here, so you add them all up. Then you take the absolute value squared, and you then do an integration over final states, and you divide by the incoming flux, and that gives you the cross-section finally. That's basically as it's done in quantum mechanics. On the other hand, you may want, since we skipped chapter 3 of Weinberg, you may want me to go through that in detail to show you what the factors are, or are you happy enough with the way you did in quantum mechanics, Fermi's golden rule and so forth?
Say that I'm happy enough with what we did in quantum mechanics.
Okay, great. All right. If you guys change your mind, let me know, but give me a few days' notice, because I don't want to. I don't know if I can actually wing it. So this is pretty much. Well, it's certainly the end of the notes for my notes for chapter 6. And so I'm not sure what to do in chapter 7. Chapter 7 is something that you can read on your own. On the other hand, I don't think I should actually skip it, so I'm going to do some of it right now. But what would you guys most like to see in the rest of the course? One thing is to do some more of the Lagrangian formalism in some detail. That's chapter 7. Then the next chapter 8 is quantum electrodynamics, which, if any of you are in quantum information theory, that's something we should certainly do. In fact, I certainly plan to do chapter 8 without any question. 9, if I remember, is path integration. That's a fun chapter, and one that I think is really physically important. And I think it's basically the way people think about, a lot of theoretical physicists think about physics in those terms now. And then I think, even though it's not in volume 1 of Weinberg, we should do something about non-abelian gauge theory. And then this, we have to do something about one-loop diagrams, which have divergences and we have renormalization. So are those basically the sort of things that you want me to do in the rest of this course?
Sure. And I think you kind of just described everything that you could.
What?
I think you just kind of described everything that you could possibly do. So
Didn't I want?
I think you kind of just described everything that you could do.
All right.
I don't know if we have time to cover all.
Okay, so let's, first of all, I really recommend you reading the introduction to Chapter 7 and the early part of Section 7.1. Weinberg wrote, is saying things very, very clearly and sensibly there. The idea basically is that if you want scattering, so you want the S matrix, well, that comes from the Hamiltonian, so e to the minus I ht. So the thing you need is the Hamiltonian. On the other hand, in a commutative theory, a priori you might not know what the Hamiltonian is. And the symmetries of the theory aren't really very apparent in the Hamiltonian. On the other hand, if you take the action, which is an integral of a Lagrange density d4 of x, the basic rule is that you want S to be invariant under various symmetry transformations. And so that means that L should either be invariant or should transform suitably. And so if you have a gauge theory, you then have a local symmetry under which L is invariant. Local meaning that a field psi L of x at x prime, well, let's not do x prime yet. This would be e to the I theta A of x Ta psi. Well, let me write this as this is a vector. Okay. This is then a matrix. This is the vector. So you have a rotation of this vector into another vector, but the matrix here, these are the generators of the Lie algebra. So you have, for example, TATB is I, F in general, CAB, TC. And theta are parameters that or angles of rotation that, or transformation that depend on the space-time variable x. This is then a local. This is said to be a local symmetry. Under the local symmetry, L is invariant. This is L of x. If you're doing gravity, then it looks more general. It's L of x square root of the absolute value of the determinant of the space-time metric d4 of x. And then what you want is that this quantity should turn into the same thing with just primes on the x variables. And so the action is invariant. In any event, it's the Lagrangian that you want to make symmetrical. And then from the Lagrangian, you derive the Hamiltonian. And Chapter 7 is about how one does that in many cases. Chapter 7 also connects quantum field theory with ordinary quantum mechanics. And in ordinary quantum mechanics, here I'll just use Weinberg's notation. We have x and t, a commutator with commutation relations are minus or plus I delta cube of x minus y delta n bar. N and n bar are type indices, or spin indices. In any event, you have a bunch of q's at each space-time point, a bunch of p's at each space-time point, and then you have these commutation or anti-commutation relations, and then of course qn of x and t, q n prime of y and t, equal times different space. So these are equal times. These are equal time commutation relations. And then the adjoint of this, or, well, it would be Pn of x and t, P, well, it's n bar, I guess, n bar prime of y and t minus plus also is 0. So these are the rules that we learned in quantum mechanics, although the fact that they're that you use the anti-commutator, that's not something that really shows up in ordinary quantum mechanics. Although I guess it sort of does, but in a funny kind of way. Now, if we start with just a scalar field phi of x, that's, let us say, what are we going to use? d4 k over square root of 2 pi cubed to the 3 halves, or 2 pi cubed here, 2k0, a of k e to the I kx, plus a dagger of k e to the minus I kx. Then what you can show is that phi of x, the commutator of phi of x and minus phi of y, so this is the commutator, this is equal to delta of x minus y. This is a new function that's closely related to the old functions. And if you write it down, you just do the commutation relation. You get 2 pi cubed, 2k0, and then you have two factors now, e to the I k dot x minus y minus e to the minus I k x minus y. And the first term is delta plus. I don't know, the second term might be delta minus, but we don't need to know that. In any event, this is capital delta without the plus sign. What we did learn in chapter 5 was that if we go to equal times here, we have delta of x minus y and no time difference. This is then an integral in which the times are equal, so x0 minus y0 cancels. And so this just depends upon 3 vector k. But on the other hand, 3 vector k, the only other place it occurs is in k0 and it occurs squared. So you can flip k to minus k and there's no change. So when there's no time component here, these two terms cancel. And in fact, the fields commute at equal time, at equal times, and that's this relation here. And we can also also take the time derivative of this expression. So for example, if we had phi dot of x, the commutator of that with phi of y, well, we'll shortly realize that phi dot is essentially, that we'll identify phi dot with the canonical momentum p, or the, in other words, if q of x and t is phi of x and t, then p of y and t is phi dot of y and t. Let's take the time derivative of this. Well, then we'll get an I k0 here. We'll also get an I k0 there. And so this will give us an I d cubed k over 2 pi cubed. The k0s cancel. And what we have here is e to the I k x minus y. But now, when you differentiate, you get a minus sign coming in, and that cancels that factor. So we get e to the plus I. So we have a plus sign here. And now, if we're talking about equal times, so in other words, we have phi dot of x and t, phi of y and t, commutator, space part for the x's and the y's. Then you see these two terms cancel. X and y are equal times, so these are just space vectors. And then you see, of course, the utility of this, of Weinberg's choice of metric, in that this just comes in as a plus sign. You don't have these extra minus signs to screw around with. Once again, we can flip k to minus k, because this only involves d cubed k. And the two terms here cancel the factor of 2. This thing is then a delta function. So this is I delta cubed of x minus y. And in fact, okay, now I'm a little concerned here. Because I wanted QP is I, I've got PQ is I. I was talking about Weinberg's metric. There's a minus sign here. This pulls down not an I, but a minus I. When you differentiate with respect to x0, you're bringing down minus k0. And so we'll rewrite this as phi of x and t, phi dot of y and t, commutator is then I delta cubed of x minus y. Of course, the delta function is even under x and y. You might worry, well, what about if we differentiate this first with respect to the time of the field at x, and then with respect to the time of the field at y? Then what we would get would be phi dot of x, phi dot of y, And so now I have to differentiate, and I've got too many minus signs to keep straight. We're differentiating with respect to the y time, so we have 2 minus i's, that brings down a plus I, and so this is integral d4th k 2 pi to the 4, or 2 pi cubed, but now this brings us a k0 and a 2, but then we have e to the I k x minus y. Now we get a minus sign again. And so once again at equal times, they actually cancel. But this is a very singular expression. So this is in fact 0, but it's a slightly scary form of 0. So it's formally 0, and Weinberg takes it to be 0. To what extent, in what detailed sense it's 0, is something that I can't say just off the top of my head. The way one analyzes things like this, by the way, is you have some singular expression. You put in test functions that are very smooth. In other words, things like e to the minus x squared minus y squared, and you multiply them times this, you integrate over space and see what you get. That will see whether you in fact get 0. Then the thing is, that's the sense in which the thing is 0. And the question then is, over what space of test functions is this singular expression 0? And I don't know, off the top of my head, I'm not quite sure what the answer to that is. Okay, so we're out of Blackboard for the moment. So are there any questions? Yes.
Yeah, for the...
Sam, you didn't get any points.
It really more so goes back to when we were talking about the symmetry. Should the symmetry be such, I mean, I guess you said such that the Lagrangian is variant, or is invariant. What if it's something that just leaves the action invariant? Is that...
Right. Okay, great question. Yes, what you want is that the action be invariant. And in fact, in general relativity, it's that L square root of G d4th x is, it's not even invariant, it's covariant, because you're changing x to x prime, and what you have is an integral, after you make a general coordinate transformation, you have the thing just looks like L of x prime square root of the absolute value of G of x prime d4th x prime. And so the action is invariant. And in the case of supersymmetry, when you make the supersymmetry transformation, this structure in here changes by a total derivative. And so then, if you assume that funding is so restricted that you can't pay for fields at infinity, then you drop the boundary terms. But maybe a better way of saying that, I'm not quite sure what it is, but in the case of supersymmetry, you do get a total derivative here. And you say, well, that doesn't affect the equations of motion, which of course is true.
Yeah.
But on the other hand, it does affect the action. And I don't know, in my mind, that raises questions. In most people's minds, it doesn't. And if we just think about path integrals for a moment, you see in path integrals, what you have is you have e to the I s, which you're then integrating over fields. So it's the action that's important. And so symmetries focus on the action. And just the way physics has been constructed historically, actions have very nice forms that are then invariant under Lorentz transformations, for example, or covariant under Lorentz transformations, whereas Hamiltonians aren't, because the Hamiltonian is the zeroth component, the time component of a 4 vector. Energy is the time component of the energy momentum 4 vector. And so energy doesn't transform nicely. So if you want to pick a nice theory, you pick a nice Lagrangian, start there, and then proceed. And the canonical way of doing that is you pick a nice Lagrangian, you compute your Hamiltonian, you then exponentiate your Hamiltonian, and you get your scattering amplitudes. That's the traditional way of doing it. Many people quite rightly go directly to a path integral formulation. They say, well, the reason that the Lagrangian is important is that the action is what occurs in the path integral. The path integral is the basic thing, not the Hamiltonian, and we should just think in terms of path integrals, forget these awkward operators and so forth. So that's another possible way of thinking. In any event, you're closer to symmetries with the Lagrangian.
Do most symmetries that are shown in the base of the Hamiltonian?
I'm sorry, say it again?
Do most symmetries show themselves within the Hamiltonian too? Because normally whenever you first learn about symmetry in quantum mechanics, you think, oh, it's like a set of operators that commute with the Hamiltonian, right? Generally call these things.
Yeah, you're
Symmetries.
absolutely right.
It's just kind of funny, I'm just trying to think of like, what's the connection.
Okay, Laura, let's think about that for a moment here. The symmetry that you're thinking about here is conservation of quantities. Things are conserved in time if they commute with the Hamiltonian.
Sure.
But now the conservation of some quantity in time normally results from a symmetry.
Yeah.
Now the curious thing here is that it's the global symmetry that gives you this conservation. And something that I said to you last time or the time before is that string theorists now think that global symmetries are simply inconsistent unless they're gauged. And so it's really a gauge. But of course, if you have a gauge symmetry, you also have global symmetry. Just let the parameters be constant and independent of time. So that's that sense.
I guess will it show up as like maybe like the no other charge or something like that?
Huh?
Will it show up as like the no other charge?
Right.
Okay.
Right. You have a
like
symmetry,
what I would do.
and that gives you, by Noether's theorem, you get conservation law. And that's a very nice bit of logic, actually, and for sure we're going to have to do that. In the few minutes that are left, let me, well, I think I'll just go directly to the whiteboard here. So over there on the blackboard, we were talking about simply real fields, but as I emphasized many times, there's Gelman's trick of making a complex field out of two fields that have the same mass. And what you do is you just do that. And then you might say, well, here is phi dagger. Whoops. So this is going to be 1 over square root of 2 phi 1 dagger minus I phi 2 dagger of x. And now, in particular, you also will have phi dot of x. Well, yeah, why am I doing x and t? Let me just do phi dot of x. This is then 1 over root 2 phi 1 dot plus I phi 2 dot. Oh, now I left out the x's. Okay. And now phi dot dagger of x is 1 over root 2 phi 1 dot dagger minus I phi 2 dot dagger of x. Okay, so what are the commutation relations going to be now? Well, clearly we're going to have phi of x and t, phi of y and t at equal time are going to vanish. Just because, well, what we're assuming here that phi 1, what we have as here as commutation relations are phi I of x and t, phi j of y and t is I delta ij delta. No, this is just 0, sorry. This is just 0. And then we want phi I of x and t, phi dot j of y and t. We know what this is. This is I delta ij delta cubed of x minus y. So now, what is the case for the complex scalar field? Well, it turns out that phi of x and t with phi dagger dot of y and t, this will give us I delta. And the way to see that is to use these formulas here. Namely, we'll have 1/2, and then the commutator will be phi 1 plus I phi 2, and then this part is going to be phi 1 dot dagger minus I phi 2 dot dagger. Okay. Well, phi 1 with phi 1 dot dagger, that'll give us I delta. Phi 2 with phi 2. Okay, hold on a second here. Oh, these are real fields. So once you do a dagger on them, it doesn't matter. So the dagger here just does that. So in other words, phi 1 dagger is the same thing as phi 1 is real, phi 1 dot is real, phi 1 dot dagger is phi 1 dot, so we can get rid of those things. So now we have phi 1 with phi 1 dot, that gives us delta, I delta. Phi 2 with phi 2 dot gives us I delta. I times minus I is plus 1, so this is plus I delta. So this gives us I delta cubed of x minus y. So the variable that's canonical to phi, in other words, the variable that's canonical is not phi dagger or phi dot, it's phi dot dagger. And the reason why you need the dagger is you need to flip this sign here. All right, I think we can stop here. Next time, I'm going to try to do some of Chapter 3. And what I'm going to try to do in Chapter 3 is to cover the stuff that's most important and simplest. There's, as usual in any Weinberg chapter, there are things that are very, very subtle and deep. And these are things that in every other book are swept under the rug and hidden, and the author will distract the reader from those things.
Thanks so much. Red Sox are 2-0.
You're a Red Sox fan?
What?
You're a Red Sox fan?
I frankly don't root for corporations I'm opposed to anything but intramural sports, frankly. I'm in favor of ordinary people playing sports, but I don't like NCAA, and I certainly don't like professional football and basketball and baseball. I think they have tax benefits that are outrageous and so forth. I'd tax them churches out of existence if I were running things. Of course, I'm nowhere near running anything. All right, I guess we're done. You might as well turn it off.